Up to this point, the techniques we've learned have worked really well with algebraic functions. We used the substitution method, we used algebraic tricks and the limit laws, and we've been able to evaluate a lot of different types of limits using these techniques. However, those techniques that we've used so far don't always work. In fact, in some of the most important trig limits that we use a lot in our calculus class won't be able to be found using those limits that we've talked about so far. So I'm going to introduce a new tool that we can put in our limit toolbox called the squeeze theorem. Now, the squeeze theorem in our textbook, that's what it's called, the squeeze theorem, but you might see in other textbooks or other places, sometimes it's also called the sandwich theorem, but it's the same thing. Now, the idea behind the squeeze theorem is actually really, really simple. Sometimes we have a function whose limit is difficult to find algebraically and to determine directly. But if we can show that this function is trapped or squeezed between two other functions whose limits we do know, then we can determine the limit of the middle function. So if we take a look at this picture here, we have the function in the middle, which is like a teal color or a greenish color. That's g of x. So if we want to find the limit of g of x, we know the limit of h of x and f of x. H of x is that dark blue above the g of x. It's the top function. F of x is in the orange, that is below g of x. And so g of x is sandwiched or squeezed between h of x and f of x. Now, because we want to find, this is what we're trying to do, we're trying to find the limit as x approaches a of this function g of x. We know what the limit is for f of x and h of x as x approaches a. They're both the same thing. So let's call both of those limits, since they're the same, we'll call them limit L. It's just some number. It could be 5, it could be 7, who knows what it is. But generically, let's just call it L. If I know that in this area, as we approach a from both directions, in that interval, that's close, that surrounds A, that's close to A, that g of x is squeezed between h of x and f of x. So we know this to be a true statement, that g of x is between or equal to f of x and h of x on this interval that's close to A. Then I can say, if I take the limit of each piece of that inequality, I'm going to take the limit as x approaches a of f of x, and then I'm going to say less than or equal to the limit as x approaches a of g of x, which is less than or equal to the limit as x approaches a of h of x. And since we're calling the limit of f of x and h of x as x approaches a, we're calling that L, it's some number. So L is less than or equal to the limit as x approaches a of g of x, which is less than or equal to the limit as x approaches a of h of x. Oops, I meant to rewrite that with an L there. Hold on, let me fix it. I meant to write L there. So if L is some number, say 5 or 7 or 100, whatever it is, if the limit of x as x approaches a of g of x is greater than or equal to L, and it's also less than or equal to L, that limit itself, that limit is forced to be L. So that tells us that the limit as x approaches a of g of x has to be L. So if we put some numbers in it, so that we can wrap our head around it, think about this statement. If I said 5 was less than or equal to x, which is less than or equal to 5, if x is between 5 or equal to 5, x has to be 5. let's now apply the squeeze theorem and find two very important limits involving trig functions. And this is very important limits that we're going to use throughout the semester. It's going to keep popping up. So once we get through these two examples, you might want to write down these limits onto your reference pages so you have that handy for your test. And of course, your homework. Okay, so we want to find the limit as x approaches 0 of the function sine x over x. We cannot use direct substitution here. I can't plug in 0 in for x because I get sine of 0, which is 0, divided by 0. So we get that indeterminate form of 0 over 0. There's nothing I can do with this in terms of algebra manipulation. So this is a good example of how we can use the squeeze theorem. So the graph of sine x over x, I sketched it here. It's a terrible sketch. If you want to see a more accurate picture, you probably should graph it on your graphing calculator because my artwork is terrible. But you'll see this curve in black. It cycles through just kind of like a regular trig function where it bounces back and forth, but it gets closer and closer to the x-axis as it goes further out. Two functions that we can use to squeeze in that sine x over x. I'm going to use different colors for this. Okay, we could use cosine of x when we're close to the value of x equals 0. Cosine looks something like this. And then, of course, it cycles through, but I'm just going to draw the sketch up close. Okay, so it looks something like that. Again, I recommend that you graph this on your calculator to see a better picture of it. And then we also can use the other function, I'll use green, as just the constant function y equals 1. Let me actually label this one. In the blue, this is cosine x. Now, if you had that on your graphing calculator and you zoomed in, you'll see right around where x is equal to 0, you'll see that sine x over x is squeezed between 1 and cosine of x. So I can say that cosine x is less than or equal to sine x over x, which is less than or equal to 1, because it's squeezed in there. Now, if I take the limit of each part of this compound inequality, I would have the limit as x approaches 0 of cosine x is less than or equal to the limit as x approaches 0 of sine x over x, which is less than or equal to the limit as x approaches 0 of the constant function 1. Now, this limit is easy to determine. That I can use direct substitution. If I plug in 0 in for cosine x, I'm going to get 1. I'm going to carry the rest of it down. I also know that the limit of a constant function is just that constant itself. So the limit as x approaches 0 of 1 is just 1. Now notice that the limit that we're trying to find is squeezed between 1 and 1. It has to be greater than or equal to 1, and it has to be less than or equal to 1. So the only value that this limit as x approaches 0 can be of sine of x over x, that limit has to be 1. So make sure you save that limit on your reference pages because you're going to need it later. Now, there might be different functions that you can squeeze it between that it will work. However, these are the functions that I'm using. And you can see when you are close, let me highlight it. When you're close and we're focused on just this area, as you're getting closer to x is equal to 0, the sine x over x function is squeezed between cosine x and 1. Now let's look at the second very important limit that you're going to see frequently in your math career. Okay, so we have the limit as x approaches 0 of 1 minus cosine x over x. If I sketch a graph of the function cosine x over x, where it's close to 0, it's going to look something like this. Not very good sketch. Again, use your calculator to get a better look at it. But what I'm going to do is I'm going to use the two functions, absolute value of x and negative absolute value of x. So this in black is 1 minus cosine x over x. Now let me add different colors here. So this function right here that I'm writing in blue, this is the absolute value of x. And let me use a different color. I'll use green. Negative absolute value of x is the same thing as the absolute value of x, but it's just flipped upside down. So as you can see from the graph that 1 minus cosine x over x, when I'm looking at the area around x is 0, that function, 1 minus cosine x over x, is squeezed between the absolute value of x and negative absolute value of x. So I can write this inequality. Negative absolute value of x is less than or equal to 1 minus cosine x over x, which is less than or equal to the absolute value of x when I'm in that area, okay, around x is equal to 0. Now, I'm going to take the limit of all three parts of this compound inequality. So I'm going to write it down here so I have more room. The limit as x approaches 0 of the function negative absolute value of x is going to be less than or equal to the limit as x approaches 0 of the function 1 minus cosine x over x, which is less than or equal to the limit of the absolute value of x as x approaches 0. Now, if I use direct substitution for those absolute value functions, I don't have any problems with that. I know that this limit, if I use direct substitution, is 0. I'm going to copy everything else down. And when I use direct substitution for the absolute value of x, I get the limit is 0 as well. Now, this limit of 1 minus cosine x over x is squeezed between 0 and 0. So that limit, as x approaches 0, of 1 minus cosine x over x has to be equal to 0. So this is the other very important trig limit that you're going to want to write down on your reference